Today on Macaulay Math, we're looking at arithmetic sequences in series. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 36 on arithmetic sequences in series. Our goals for today. We're going to find the terms in a sequence both explicitly and recursively. We're going to find the equation of the apparent nth term of a sequence. We're going to understand the meaning of n factorial. We're going to determine if a given sequence is arithmetic. We're going to use an explicit definition for arithmetic sequence to find the terms of the sequence. We're going to use the common difference to find the explicit equation for an arithmetic sequence. In this lesson, the topic of sequence and series is discussed. Applications of sequences and series involve tracking patterns, tracking how disease travels through a population, saving for retirement, tracking how to pay off an installment loan are all types of real-world applications that require the use of sequences and series. Let's get started. Let's start with the definition. A sequence is a set of numbers that are related in some way. Each number is an element or term, and they're usually listed a sub 0, a sub 1, a sub 2, a sub 3, a sub 4. A lot of times they'll start with a sub 1, sometimes they start with a sub 0, but I did want to show you all of those together. Sequences can be defined explicitly, that is by an equation where you just plug in the term number and calculate it. And sequence is defined explicitly. Give an equation to find the nth term of the sequence. That is our standard plug and chug version. Let's say I wanted to find the 10th term. I could take 10, plug it into this explicitly defined sequence, and I could calculate that term. Sequences can also be defined recursively, and that's a little bit different. Sequences that are defined recursively have the first or the first few terms given, and then an equation that finds the next term based on the previous term or previous terms. And so for a recursively defined sequence, you have to know the term that came before it or possibly a couple of terms that came before it to calculate the next term. Now, you may ask yourself, why would I ever define something recursively if I have to calculate each term individually? Well, some sequences can only be defined recursively, and I will show you an example of that here in a moment. But we have here an elementary example, and basically this is an example that could be defined explicitly, but they tell you what a sub 1 is. It's 4. And the example asks us to find the first 5 terms found recursively. Well, if I make a list of those terms, they already give me the first one, so I only have to calculate 4 more. If I want to calculate that second term, that would be a sub 2, the second term. So in this formula that I'm going to use to calculate the next term, n is 2, so here I would have a sub 2 minus 1 times 4. Well, 2 minus 1 is 1, a sub 1 times 4, and I know what a sub 1 is. I was given it. A sub 1 is equal to 4, so I have 4 times 4 is 16. The second term is 16. A sub 3. That would be the third term, the next term that I'm trying to find. And it would be a sub 3 minus 1 times 4. 3 minus 1, a sub 2 times 4. 16 times 4 is 64. The fourth term, a sub 4, would be a sub 4 minus 1 times 4. Which would be a sub 3 times 4, which is 64 times 4, which is 256. And the last term, a sub 5, would be a sub 5 minus 1 times 4, which is a sub 4 times 4, which is 256 times 4, which is 1024. And that is our set of the first 5 terms. Now, here's the thing. If you guys see the pattern, you don't have to write all these out. just do the first couple, and then once you see the pattern, go ahead. Now, the Fibonacci sequence is a recursive sequence that cannot be expressed explicitly. And if you want to see a neat little talk about Fibonacci numbers and how they exist in nature, a lot of things in nature are a Fibonacci number, usually like the numbers of fingers and toes that an animal has, the number of rows on an ear of corn, the number of petals in a flower is usually a Fibonacci number. But in this case, they give me the first two terms in the sequence. Then it gives you an equation that says your next term is found by taking the two terms before it and adding them together. So if I'm writing out this sequence here, my first term is 1, my second term is 1, that is given. A sub 3 would be A sub 2 plus A sub 1. And I'm skipping a step from the last one because hopefully you can see that 3 minus 1 would be 2, and 3 minus 2 would be 1, which would give me 1 plus 1 is equal to 2. And then A sub 4, and this is the last one that I'll do this way for this one, would be A sub 3 plus A sub 2. And we just calculated A sub 3 to be 2. And then we know that A sub 2 is 1, so when I add those together, I get 3. And the next term, and if you see the pattern now, you take the two terms before it, and you add. 3 plus 2 would be 5. 5 plus 3 would be 8. 8 plus 5 would be 13, and it goes on from there. And again, you can see some numbers that exist in nature. Humans have 5 fingers and toes. Octopus have 8 arms. As we can see, Fibonacci numbers occur quite often in nature. The next definition is factorial, denoted with an exclamation point. And n factorial is the product of the integers from 1 to n. And I usually do them in reverse order. So as a elementary example here, I have 5 factorial. That would be 5 times 4 times 3 times 2 times 1. 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. 120 times 1 is 120. You can do that in Desmos as well using just the exclamation point. And so if I go 5 and then shift 1 to get my exclamation point, I have 120. Also note that 0 factorial is a special case definition. Anytime you see 0 factorial, it is 1. That is necessary for a concept in probability and counting for permutations and combinations, which you probably saw in statistics. Okay, summation notation. This is something new. This is a way that you can add up the first n terms of a sequence and write these sequences a little bit smaller because the sequences and the series can get big very quickly. So what this basically says is you'll have a formula or something to calculate A sub I, which would be the terms in your list of your series here. And basically what you're going to do is you're going to plug all of the numbers from whatever's here to whatever number is up here into this formula, and then you'll add them all up. And the terms that we use this little I here, we call that the index of summation because that is the variable of that formula. In this case, 1 is the lower limit of summation, and 1 is usually the lower limit because that's how we usually count. We usually start counting 1, 2, 3, 4, 5. We don't usually count 0, 1, 2, 3, 4, 5. But it doesn't have to start with 1. It can start with whatever number it wants to. N is the upper limit of summation. Again, you plug in all of the counting numbers from the lower limit to the upper limit into the formula. Some properties of summation notation. If you take the sum of the first n numbers of some constant c, then the value of this will be just c times n. And that makes sense. If I had c being 2 and n being 10, if I add up 2 10 times, it would be the same as 2 times 10. If you are multiplying every term in a series by a constant, you can factor that constant out. If you are adding up a series that is based on two formulas, you can calculate the sum of the first formula, calculate the sum of the second formula, and then add those together. Similarly, if you're subtracting, you can do the sum of the first series, do the sum of the second series, and subtract those values. Definition: consider the sequence a sub 1, a sub 2, a sub 3, a sub 4. The sum of the first n terms of the sequence is called a finite series, or an nth partial sum of the series, which can be denoted by a sub 1 plus a sub 2 plus a sub 3 plus dot 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 all the way up to the nth term. And then you can write this entire series using summation notation, as long as a sub I is an explicit formula. And then the sum of all of the terms in an infinite sequence, called an infinite series, can be denoted by this thing, which goes on forever, from 1 to infinity of a sub I. Most of those sums are unbounded, but there are instances where you could add up an infinite number of terms in a series and get a finite value. We'll talk about that in the next lesson. An arithmetic sequence is a sequence that we're going to talk about specifically today. In an arithmetic sequence, the definition says that each successive term has a common difference, meaning that every time you move over, you're going to add the same number. And when they say common difference is 2, 9 minus 7 is 2, 7 minus 5 is 2, 5 minus 3 is 2, 3 minus 1 is 2. The general equation for an arithmetic sequence is denoted by a sub n is equal to d times n minus 1 plus the first term, a sub 1. D is the common difference. And so if I were to find the general equation for this arithmetic sequence, I would say my common difference is 2, so I plug in 2. I would say that my first term is 1, so I plug in 1. I distribute and add, and I get a sub n is equal to 2n minus 1. And I do want you to note that this function is linear. All right, the general equation for arithmetic sequence is always going to be linear, and we can use that fact in some of the problems that you're going to see later on. Partial sum of a portion of the terms in a sequence. As an example, the fifth partial sum would be the sum of the first 5 terms in a sequence, and then the general finite arithmetic series, the sum of the first n terms in a sequence. You need to know the number of terms, that'll be n. You need to know the first term of the series, and you need to know the last term of the series. You add that up and divide by 2. There's a fun anecdote about Carl Friedrich Gauss on how this formula was developed, and if you want, remind me in class and I will tell you in class. So our first example, give the first 5 terms of the following sequence using a graphing calculator. This sequence here is not arithmetic, but what we can do is we can set up a table in Desmos to help us calculate this. So let's go over to Desmos and let's type that equation in as a function. So let's go f of x is equal to 1 plus parentheses negative 1 close parentheses raised to the x power, and let's put parentheses around the whole thing here so that when I hit the divide bar I get all of that in the numerator. And let's put 2x in the denominator. And you see I got a bunch of dots here. This turns out to be discrete, but we want to figure out some of the values in here, and we're going to use Desmos to do it. Now, the reason that I typed it in as function notation, if I want to make a table here, and I want to change this to f of x1, and the way you get the subscript 1 in here is after you type in x, without hitting any other buttons, just immediately hit the 1. But if I want the first 5 terms, I'm going to go 1, and then I'm going to go 2, 3, 4, 5, and that is a quick and easy way to plug in a bunch of numbers into a formula that you have been given. So I go back to Desmos here, go back the slide, and we're going to make a list of those numbers from this table, and I end up with 0, a half, 0, a quarter, and then 0. And that goes on forever, but that's the first 5 terms. Example, given the following recursive definition, find the first 5 terms of a given sequence. And again, when they give you a recursive one, they tell you the first term, put it in. Don't do any more work than what you have to do. Now, a sub 2, I did it a little bit different here. So 2 is k plus 1. That means this would be just a sub 1 plus 3. And a sub 1 is 2, so I got 2 plus 3 is 5. A sub 3 would be a sub 2 plus 3. And a sub 2 we found to be 5 plus 3. That's 5. Gives me an 8. And I see the pattern. So since I see the pattern, let's not waste our time. And 2 plus 3 is 5. 5 plus 3 is 8. 8 plus 3 is 11. And then 11 plus 3 is 14. And that is our solution. All right, next. It says expand the following summation notation and then find the sum. All right, so this one isn't too big, and you'll see that they could easily become quite large. But for us, this thing asks us to plug all of the numbers from 1 to 4 into I squared, and once you've done that, then add them all up. So this is equal to, I take 1, I plug it into I squared, I get 1 squared. 1 is not 4, so I go down here, I add 1 to it, that's 2. 2 squared. 2 is not 4, so I add a number, that gives me 3. 3 squared. 3 is not 4, so I keep going. Next number is 4. 4 squared. Now 4 squared is the upper limit, so we are finished. Now we're going to calculate these. I get 1 plus 4 plus 9 plus 16. And then 1 plus 4 is 5. 5 and 4 is 14. 14 and 16 is 30. Additionally, you can do this in Desmos. If you go to Desmos, and there are going to be some times I'm going to ask you to show your work, but if you type in SUM, it will give you summation notation. Now, you can also find that in your functions list. If you scroll all the way down near to the bottom, you'll see here summation. So that will work as well. But this seems to be easier to me. And I want to go from 1 up to 4. And then here, so they use as their index n. So I need to use n. And I need that to be n squared. And there you see that we get 30. All right. Next example. All right. It says write the following series in summation notation, and so I want to start by writing my sum. I'll use I equals 1. Now to get this upper limit, I need to count my terms. I got 1, 2, 3, 4, 5 terms. And since this is a fraction, sometimes it's easier to write those fractions as an equation for the numerator and then an equation for the denominator. And I think that's going to hold true for this case as well. So I have 1, 1, 1, 1, 1 on the top, so it never changes. I'm just going to put a 1 up there. Now, hopefully, you recognize from the last example that 1, 4, 9, 16, and 25 is just our counting values squared. So I'm going to take that I, and I use an I because that is our index. I'm going to put square around that, and 1 over 1 squared is 1 over 1. 1 over 2 squared is 1 over 4. 1 over 3 squared is 1 over 9. 1 over 4 squared is 1 over 16. And 1 over 5 squared is 1 over 25. That is my final answer. All right. Next one here. It says, in a given arithmetic sequence, the 4th term is 10 and the 6th term is 16. Write an explicit formula for the apparent nth term of the sequence. All right, so first they tell us that it's an arithmetic sequence. And we know that when we're finished, we need to have an equation that is a sub n equals
d times n minus 1 plus a sub 1. They give us that the fourth term is 10 and that the sixth term is 16. But I need a common difference and I need a first term. Well, if you recall from earlier, I made a big deal about the fact that this equation here is a linear function. So all I am going to do is I am going to say, hey, I have 4, 10, I have 6, 16. Let's just write a linear equation. Let's make a point. I got 4, 10 is 1 point. I have 6, 16 is a second point. I can find a linear equation for these values. If I find my slope, remember your slope is y2 minus y1 over x2 minus x1. And so I'll have 16 minus 10 all over 6 minus 4. That gives me 16 minus 10 is 6. 6 minus 4 is 2. That gives me 3. And then I can use the point slope formula. Remember your point slope formula. Y minus y1 equals m times x minus x1. And we'll plug in for that. We'll use the first term here. We'll go y minus 10 is equal to 3 times x minus 4. And I'll distribute. So y minus 10 is equal to 3x minus 12. And then I'll add 10 to both sides. And I'll go y equals 3x. And then it'll just be, when I add negative 12 plus 10 will be negative 2. And I just need to convert it into this form. And you'll notice that my final answer, a sub n is equal to 3n minus 2, is a nice, neat equation. And you'll notice that the common difference in the arithmetic sequence is the same as the slope in the original one. All right, last example. It says find the sum of the first 300 positive even integers. So I want to add up the first 300 even integers. So I want to go 2 plus 4 plus 6 plus 8 plus ... until I have 300 terms. Now, this one's a pretty easy one, and I will grant you that. So I'm going to do it as if it were a harder one. The 300th positive even integer is 600. All right, but we want to calculate that. So I'm going to start with that formula. A sub n is equal to d times n minus 1 plus a sub 1. Clearly, this series has a common difference of 2. So I'm going to go a sub n is equal to 2 times n minus 1 plus 2, the first term. Distribute 2n minus 2 plus 2. A sub n is equal to 2n because these two cancel. And we can calculate the 300th term by going 2 times 300 gives me 600. Now, they want me to add up all of these numbers. There's 300 of them. I could do it in decimals, but that would be a lot of work. So let's go back and let's use the formula that they give us back here that says if I have an arithmetic series and I know how many terms there are, I know the first term, I know the last term, I can calculate the sum of those values. So what we'll do is I'll start with that s sub n is equal to n times a sub 1 plus a sub n all over 2. And I know that a sub 1 right here, a sub 1, the first term is 2. I know that there's 300 terms, so that's going to be my n. So s sub 300 will be equal to 300 times the first term, which was 2, plus the last term, which is 600, all divided by 2. So I get 300 602 all over 2. And that's a big multiplication, so let's grab Desmos. And since there's an operation in the numerator, let's go parentheses 300 times 602 all divided by 2, and I get 90,300 as the sum of the first 300 positive integers. All right, that is all I got for today, folks. So, Star Wars fun fact of the day. Darth Maul has 10 horns on his head. Originally, they were meant to be feathers, but the art department misinterpreted the concept art, and I think he looks way more menacing and mean and nasty with horns. He would look a little wimpier with feathers, but again, what do I know? Just a math teacher. That is all I have for today, folks. You have a great day. Goodbye.